Hello everyone. Today is our day 12 of our long 6 days marathon on linear algebra for AI and ML. I am your host Hassan Al Banna Himel. Today is May 24th, 2024. Uh, so, without further ado, let's jump to our today's session. So, what we had learned earlier on the day 7 we have learned on basis the orthogonal vectors, the orthonormal vectors, the generic tensor notations, and on the day 8 we learned about tensor transposition, basic tensor arithmetic, tensor reduction, and the dot product. On day 9 we learned about solving linear systems with substitution, solving linear systems with elimination, and the Frobenius norm. And on the day 10 we learned about affine transformations, eigenvectors, and eigenvalues, and we also saw some code on NumPy or how to do the eigen transformations. And yesterday or on day 11 we had seen about eigen decomposition, applications of eigen decomposition, and today in today's session we will be looking at data compression with SVD or singular value decomposition, and finally we will conclude our today's session or our long 6-day marathon sessions with the Moore-Penrose pseudo-inverse. So let's jump to our today's topics. As said earlier, today we will be covering data compression with SVD or singular value decomposition, and we will be concluding with the Moore-Penrose pseudo-inverse. So let's start. Let's start with data compression with SVD. So what is SVD? By the definition, SVD is a matrix factorization technique where a matrix A is decomposed into three matrices U and diagonal matrix and V, such that A U summation V transpose. It will be a transpose represented as U will be an orthogonal matrix containing the left singular vectors, a diagonal matrix containing the singular values, and V will be an orthogonal matrix containing the right singular vectors. Let's jump to what are or how we can code these problems. We're doing this in our Google Colab. At first, let us connect this. Yeah, so it is connected. At first, let's import NumPy as usual, NumPy as np, and then we will be importing our matplotlib. Now we're doing image compression via SVD. So for this we got a PIL. From PIL we will be importing image. Now let's import. Yeah, now we're doing this with an image from GitHub. This is we got our image. Now let's open this image. It will be plotting this image. As you can see, this image is plotted in a two tensor. So it is a matrix. Here in the y-axis we got 4000 axes, and on the x-axis we got 3000. Now we all know that here is different kinds of colors, and all these colors are combination of red, green, and blue, or we also know this as RGB. So it is pretty much hard for us to define this with this much color standards. So for our better understanding, we will be transforming this whole photo into a gray and white. Let's turn this. Yes, so you can see that our this colored photo is transferred into a grayscale photo. Now we will be dividing this into some parts. When I do this, uh, it is more detailed now. This is now divided into parts. Now we are doing the SVD or U, sigma and V here for this photo. uh, it is taking some times. Yeah, now this cell has run, and as eigenvalues are arranged in descending order in diagonal, so two are singular values. By convention, arranged in descending order in D or in this code diagonal, thus the first singular vector and the right singular vector of V may represent the most prominent feature of this image. So for this, we are multiplying, finding product of our the first left singular vector and our sigma value with our first right singular vector. So now let's plot this again in gray, reconstruct this. You can say that you can find the proper image of this dog with book here anymore. Here you are seeing some gray and white and black something, right? So now to additional, we're adding some singular vectors to improve the image quality. Let's do this one. We will be doing for two singular values. We will be doing it for 4 and then 8, then 16, then 32, then 64, then 128, and finally 248. As you can see that when it is 2, you can't say either that what is it. You can say what it is or what it is saying or what is in this picture. When here 4, you can say that there is something, right? We can say that there is something present in this picture. I can see something. And when it is 8, you can now tell that here is an animal and there is an object like thing. Now when it is 16, you can say more perfectly or precisely that here it is a dog and here it is a book. Now when it is 32, you can say more perfectly here it is a dog and here it is a book named Deep Learning Illustrated. And when it is 64, it is more accurate. When it is 128, the picture is more perfect. And when it is 248, you can see the picture is almost high definition quality. So you can see that when it is moving forward, it is enriching or it is improving its quality. When it is 2, you can say like what is this, like this is nothing, what is Himmel teaching us, this is something crap like things. And when we're doing it 4, it is more relevant. When it is 8, it is uh, getting better, right? And then 16, more better. 32 more better, 64 it is getting better, 128 more better, and in 248 it is better than before. And uh, let's do the calculation with 64 singular vectors. The image is reconstructed quite well, right, in the 64 singular vectors. However, the data footprint is much smaller than the original image. Now let's shape this. Here we can say it is 4032 and 3024, and to find the full representation we will be multiplying our 4032 with 3024. We will be getting 12192768, and to get the SVD representation it is giving us 451648. To find the percentage we have run and we got 0.037, or we can say it is 3.7%. Specifically, the image represented as 64 singular vectors is 3.7% of the size of the original. Alongside images, we can use singular vectors for dramatic lossy compression of other types of media files. Now let's again move to our slide. So we have seen that how we can use data compression with SVD. We have learned in hands-on code with NumPy, Matplotlib, and with our PIL. Now, what are the benefits of using this? Reduced storage. The compressed matrix AK requires storing fewer elements than original matrix. And we can also do data reconstruction. Original data can be approximated and reconstructed from the compressed version with reduced dimensionality. And it also do the noise reduction, often helps in denoising the data by keeping significant singular values and ignoring smaller and noisy ones. And what is the key considerations? In each things we got some considerations, right? So what are the key considerations here? It is number 1 rank selection, number 2 computational efficiency, and number 3 lossy compression. In the first one, choosing the appropriate value of k is crucial for balancing compression and reconstruction accuracy. And here in the computational efficiency, we can say that SVD computation can be intensive for large matrices through efficient algorithms and approximations exist. And finally, on the lossy compression, SVD compression is generally lossy, meaning some information is discarded during the truncation process. That was for the image process using SVD. Now let's move to our next and final topic for our this marathon, and which is the Moore-Penrose pseudo-inverse. So what is a Moore-Penrose pseudo-inverse? The Moore-Penrose pseudo-inverse of A of a matrix A is a generalization of the inverse matrix that exists for any matrix regardless of whether it is square or non-square. And how we can write it down? We can write it like A plus equal V D plus and V transpose. So what is the uniqueness? The pseudo inverse is unique for any given matrix. Now again, let's see some coding problem again. Here we have seen this one. Yeah. For the Moore-Penrose pseudo inverse, let's at first get an array. Here we are using an array A, and the array shows us minus 1 2, 3 minus 2, and 5 7. And then finally we get our transpose matrix here, u d v transpose. Our u will be this array of a 3 by 3 matrix. Our v transpose will be an 2 by 2 matrix, and our d will be an array consisting two elements. Here we have an 8.66918448, and another element is 4.10429,538. To create the d plus, we first invert the non-zero values of d. So we can do this in diagonal, and after getting this is here, we can see the main trace, or our main trace will have the elements, and the other two values will become 0. And then we would take the transpose of resulting matrix, because D is a diagonal matrix. This can, however, be done in a single step by inverting D. Now let's invert our D. When we invert, we will get 0.11535511, and our second element will be 0, third element will be 0, and final element will be 0.24364718. And the D plus will be our np dot concatenate our D inverse, our np array, and the axis of 1. So it will be give a 2 row and 3 column matrix. And finally we will do the dot product. How we can find the dot product? We know all that we need to do the transpose, and we can pass more than two values in a single dot product. So in first we will be passing one, and on the second one we will be passing another one. So we will be getting an array of 3 columns and 2 rows. Working out this derivation is helpful for understanding how Moore-Penrose pseudo-inverse works. But unsurprisingly, NumPy is loaded with an existing method P inverse. So when we do this, we will get our desired value. So unless we can do this, we can also do this one to get the pseudo-inverse more precisely. Now let's back to our slide again. So what are the applications of Moore-Penrose pseudo-inverse? It can help you to solve the linear systems. It can used in data fitting, in signal processing, control theory. How it can be helped in solving linear systems? It used to find least square solutions to linear systems, particularly when the system does not have a unique solution. It also helps in data fitting, employed in regression analysis to determine the best fit line or curve. It also helps in signal processing, applied in various algorithms for signal reconstruction and noise reduction. It also used in the control theory, used in the design and analysis of control systems. What are the properties and characteristics? In the generalization, works for any matrix, not limited, only limited to square matrices. You can use it any dimension of matrix. You can use it in a column matrix, in row matrix, in any kind of matrices. It is not only limited in square matrix, like you only need a 2 by 2 matrix, or you only need a 3 by 3 or 4 by 4 matrix. It is not limited, right? You can use this method in any kind of matrices. And on the our point 2, it is least square solution, provides a minimum norm solution to our equation ax is equal b. And finally it gives our stability. The pseudo-inverse can help in stabilizing solutions in numerical computations, especially when dealing with ill-conditioned matrices. So that was for our today's session. So we have concluded our marathon, our 6 day marathon. So we learned many things, we covered many things in these 6 days, and there will be another final session on this Thursday, final session on linear algebra for AI and ML. So see you guys there. Thank you, everyone.